It is my pleasure to introduce to you Dr. Ming Qu. She has already given a few seminars to us, and they're always very exciting and informative. So she is presenting this month's AnalytiXIN Manufacturing Data Asset Seminar. Dr. Ming and your team, the floor is yours.
Okay, thank you, Rhea. Yeah, I will ask my student DK to share the screen so we can present. Okay. Thank you everyone to join us for today's seminar. Today's seminar really focused on our past year and actually for our work on the building analytic models. So this is one portion of our Purdue team on this manufacturing facility energy optimization, the whole entire model that's a part of it. DK, please move on. Okay, so today's seminar, we're gonna cover 4 major areas. They are data collection and the data processing and our models and also the future work. First, let me introduce my team. So myself is a professor in the Lines School of Civil Engineering at Purdue. I have a PhD student, DK, here. So he is a first-year PhD student. He works on the building thermal modeling. Then I have Andy Zhang. He is a master student from mechanical engineering at Purdue. And also we have our younger team member, Kayla. Actually, she goes through the Reach Out program. So she is a sophomore in the West Lafayette Junior Senior High. Yeah. Okay. Let me first talk about the big overarching goal for our project. So for Purdue, we are aiming to develop advanced energy models and analytics for energy audit and optimization, dedicated for this advanced manufacturing facility in the Indiana state and beyond. So for our portion, we focus on the building energy model and analytics. So our goal is trying to develop a real-time building energy analytics model. So this model can forecast the energy performance, right, by leveraging our streaming data, also control and artificial intelligence, some method for our energy system. So our goal is trying to reduce the building energy consumptions related to building, right, 20 to 30%, and also have capability of demand response. So we are able to reduce the building peak load at least 50 to 60%, kind of shift load away from the peak time. So our case study is actually this Emerging Manufacturing Collaboration Center. So we call it EMC Square. So next slide, please. So this is our facility, EMC Square, as everybody knows, is located in the Indianapolis. So the total area about 60,000 square feet. So its orientation is not due north, a little bit away, like a 30 to 45 degree of the due north. So this facility is the entire project, basically the test bed, prototyping, demonstration facility, both in hardware and software. So currently we have all kinds of sensors installed in this building, and also it's still ongoing. Sensors will install on the machine inside of facility. So the entire data sensing and data are actually from both wireless and a wire-based system. So our industry partner actually integrated all those data from different type of the network into the cloud base. So through this global project, software and hardware, so it's able to upload all the data to Amazon AWS cloud server. Then so that's the data we have S3 buckets available for us to get the stream data from AWS server. So good news, our team, I mean Purdue team, the group work on the data lake already successfully make the lake flow. So that means the data right now can get it from, so we can get it, the stream data from AWS platform, then it's automatically converted to the format, the data that we are, we like, I mean, engineers would like to have, which is not the tag, like a time tag type of the data. We sort them or rearrange them into the sub tables, which we can directly use for our modeling and some other analytic work. So so this data lake is already available right now. So we are in the process to integrate our model with this data lake very soon. So our model is really work on the this Colab. We use the Google Colab to code our models. Yes, please, next slides. So next one, I'm going to talk about the energy audit. The first step, we actually carry on the site visit last year in fall. So the goal of the visit, so we want to understand the physical building siting, especially the thermal, the building physical physics, and also the building energy system. So our vision for this site visit in the more broad application, we're going to generate so-called virtual site visit in the future. So our platform can plug in the local site facility siting direct through the virtual touring. We're going to have some kind of guidance for the later on virtual site visit to kind of gathering the most important information of the local building physics. So as you can see, we visited our the EMC square buildings HVAC system, also the user spaces like office area and the manufacturing areas. So at the lower row of the pictures are the basically the local HVAC control system, and some hardware, the air handling unit. Next, please. So except the on-site visit, we also installed some sensors for our modeling work. So we have installed 4 temperature sensors on the 4 different 4 external walls. With different orientation, basically, as you can see, the 4 orientations. So we install them on the surface of the inner wall, and also get adjacent air temperature very close to the wall. So those temperature measurements are very important for our building thermal model. We will talk about later, which is RC model. So this is truly trying to get our later on the AI model, more accurate AI model to prepare for that step. And additionally, we installed a rooftop weather station so we can get a more closed weather conditions for our model, because the weather conditions plays a significant role in the building performance. So as you can see in the picture, right, at your right lower corner, This is a picture of our thermocouple, very tiny probe, and we stick it on the wall. And at the left lower corner is our weather station, which has the wireless communication capability. Next, please. So this is the just to show all those new installed sensors are already integrated into existing data collection and also become streaming data available, and we convert them to the way we engineers are familiar with, which is you can really read the trends of this data. So as you can see clearly, the wall surface temperature on the inner wall surface temperature is relatively like a 2-degree difference lower than indoor. This is in December, which makes sense. This is also as we expected. Okay, thank you. And next, please. DK, next slide, please. Yeah, so I will hand over to DK, talk about the work he has done to process data and make it ready for our models. DK, go ahead, please.
Thank you. So after the data collection, we upload all the data to this AWS S3 bucket. This is the structure of files in S3 bucket. There are 2 main folders. The first one is called metadata. It stores all the information of the assets separated into 122 ND-JSON files. And within all the asset groups, the only thing that matters to us is the EMC square. And it has these labels. In total, there are 33 assets in the EMC square, and we are using this asset information combined with the property updates to get all the data that we want. In this property updates folder, there are several levels of subfolders from year down to minute. And for each minute, the operation data of the EMC square stores as a Pocket file. Within all these labels, there are only 6 columns that are useful for us right now, which are the time, the names of the assets and the properties, and data type, value, and unit of the measured parameters. So in order to combine the information of the ND-JSON files and the Pocket files, we create connection between them using this asset ID and asset property ID. Making this connection is the first step in the data preprocessing. The data preprocessing program that we developed is used to prepare the data set in time series, and then we can later use the data set in our models. So in the program, we access the data in the AWS using an SDK called Boto3. And from the metadata folder, we grabbed all the information and created an asset list. Kayla will introduce to you how we visualize the data set using this asset list. Then from the property updates folder, we can get the operation data of the EMC square. Since the whole data set is huge and we only want several assets that is useful for our model, so the program is capable of letting us select a specific time range that we want and assets that we need. When the reading of the original data set finishes, the lumped data set will look like this. The indices are simply numbers, and the columns are the 6 useful columns that I mentioned earlier. The next step is to reshape the data frame using time as an index and different properties as columns. In this step, we also did data cleaning and resampling. So the program will Then finally, we'll generate a CSV file for each data set and output it to Google Drive for future use. One feature that we want to add to the program is to make the selection of the time range and assets more user-friendly so that the user can simply check some boxes or select from drop-downs. Next, Kayla will show you the visualization of the data set. Kayla.
So the software that we used for this data visualization is Neo4j. And in a nutshell, Neo4j is a graphing software that is able to show the hierarchy relationship between the data. So we use the data from DKI's CSV files, and then we represented them in this graph. So in an overall diagram, we use the size of the bubble to correspond to its place in the hierarchy. So for example, the giant central bubble, the blue one there, represents the HVAC system, linked by smaller bubbles representing asset properties. We also use various colors of bubbles to represent the parameters, the data types, like for example, integer, double, or string. And so we connected our database directly to a data structure used in Neo4j and automatically created such graphs. So the significance or the importance of this graph is that it can allow us to see more clearly what our data looks like. It's also much easier to understand what assets and parameters are involved in the study in a more visual manner. And as you will see in later slides, we also created another 2 diagrams dedicated to our thermal building model and energy system model. So we also hope to utilize this to provide said more user-friendly interface for people looking to customize their manufacturing. Next slide, please. And so this is a zoomed in look of the graph on the previous page. This just allows you to see more clearly how the Neo4j software represents the relationship between the data.
Okay, so I want to chime in, really give you overall the pathway that we are doing right now. So this entire manufacturing facility environment are highly stochastic and influenced by the outdoor conditions and also occupancy behaviors and the machining equipment. So we know the building energy model actually need to communicate all those parameters and inputs. So that's why at the left side in the box, so we have a lot of inputs, and also our model will have output to the later on developed models. So for the time being, we started with our own model, but we leave all those communication input and output later on to update our model. So currently we split our building energy model in 2 submodels. So one is focused on the building physics, which we call it the building thermal submodel. That's DKI has been working on based on the kind of very rough physical principle of the building physics. The second submodel is around the building heating, cooling, ventilation system. We call it energy system submodel. So Andy worked on this. So mainly using machine learning technology to learn the relationship between the actual the equipment and the building energy consumptions. So next I will hand over to I think it's Andy, right? Andy will talk more about his heating energy model. Go ahead, Andy.
Thank you, Professor. So this is a visualization of the data set for the heating submodel. Thank you for Kayla for providing this diagram for us. Once again, going over a bit about what she said earlier, we have the boiler in the blue, which is providing the hot water for the air handling units that are shown in orange. Within air handling units, the hot water is heating up the air, and you see these smaller nodes that are pointing towards the air handling unit. These are representing associated processes that we have data on. For example, the return air temperature. Next slide, please. So there are two models that we built. There's the artificial neural network and support vector machines. I'd like to do an overview of both of them just to give you guys an introduction. So for the artificial neural network, we built this with the Kira sequential model, and we specified the number of hidden layers to be 5. The neurons per hidden layer was dependent on the number of inputs we had, as this could change depending on something known as the correlation score that we will be exploring later on in the presentation. So in short, the neurons per hidden layer is scaled by a factor of 4.2. We also used a ReLU activation function because in general, it's converging better for deep learning. It introduces nonlinearity into our learning model, which is needed for complex patterns, can be assumed to be the case for our energy model. It also avoids the vanishing gradient problem. Why did we use an artificial neural network? It's good for complex nonlinear data. And a lot of the literature that we read before we started working on this was comparing the performance between this and a support vector machine. So we wanted to have sort of a baseline to compare the two with. Next slide, please. So for our support vector machine, we built this with sklearn. We were uncertain about the data characteristics, so we tried multiple different kernels, linear, poly, and RBF. As expected, RBF generally performed the best. Next slide, please. This is going to show you the inputs and outputs that we use. For the particular inputs that are listed here, this is going to be for our December data set. So some input parameters are coming from streaming data, such as our weather station. Others are being calculated from inputs that were shown on the bubble diagram. The available data that we have worked on so far was from November, October, and December. However, the most complete data set and the one that we found the best results with was December, and it's also the most recent. So that's the one we used for this update, and that's what you'll be seeing throughout this presentation. This is a general implementation of the model in 5 steps. The first step is to load your data. The data file that we're using is a CSV file, and whether you do need to make some adjustments to it, such as adding day of week as an input parameter, and whether or not you do this before the CSV file or after, the code is going to be able to handle that. Step 2 is to identify input and output parameters. This is where the user input comes in. We're going to use a correlation matrix, which will be explained in the next slide, to specify the inputs, and the user also needs to specify the output here. Step 3 is to pre-process this data. This includes splitting the data set into test and training sets, also feature scaling. Step 3 is very standard for machine learning models. Step 4 is really a bulk of this. It's going to be building, training, and analyzing both models. And then step 5 is to generate regression figures. And, to be added to step 5 would be to add, generate any other kind of figures that we need. But for now, we stuck with just regular regression figures because that's giving us, results. But that can change in the future. So the correlation matrix, this is what was generated for the December data set. And what this is doing is giving you a correlation score for each pair of variables. And this correlation score is going to be between -1 and 1. -1 representing a strong negative correlation, while 1 represents a strong positive correlation. For example, consider the labels that I have outlined in green here. We have energy consumption and heating water return temperature with a correlation score of 0.35. What we can conclude from this is that these variables have a moderate positive correlation. So maybe you include them in the model, depending on how the rest of it looks. Next slide, please. So user input, and this is also a part of step 2 here. The code will prompt the user for a minimum correlation value to use and an output parameter. Why do we need to know the minimum correlation value? The code is going to use this minimum correlation value to find the appropriate input parameters and automatically load them up for you. The output parameter also needs to be specified for the code to do this step. For most of our uses, this output parameter is just going to be energy consumption. The figure on top shows what the user is seeing and how he's interacting, how they're interacting with the code. And then the bottom part is a little print statement before going on to step 3. It's kind of a sanity check just to make sure this is what your Y parameter is and these are what your X parameters are before you move on, just to double check. Next slide, please. So we skipped over step 3, which is the data preprocessing, because we're more interested in the accuracy of the models for this presentation. So this is step 4. All in all, we're using R² as an accuracy metric. This is going to give you a value between 0 and 1, where a higher score represents a better model. I've converted this to percentages, so think about it between 0 and 100%. As you can see, the artificial neural network is doing slightly better than the support vector machine by less than 1%. But in general, the support vector machine with the RBF kernel is performing better than the other ones. Next slide, please. And then step 5, these are the regression figures that we're able to generate for both the artificial neural networks and support vector machines, or in this case, support vector regression. I have a figure generated for each of the support vector regression models that have for each kernel, but I'm only showing on the right the figure that was generated for the RBF kernel with the R squared of, again, 89.98%. On the left, we have the same figure, but for artificial neural network with R squared of 90.69%. In general, the x-axis is going to be the actual energy output, and the y-axis is going to be the predicted energy output. We want to see values that hug this line in the middle. And then I want to pass it back to Kai to talk about his model that he developed. Next slide, Kai.
So next, I will show you the building thermal model that we developed. The data from HVAC system plays an important role in this building thermal model that we developed. So here is an example of the HVAC system terminals. The air handling unit 1 in the EMC square is responsible for the thermal condition of the areas that has the most occupants. For example, in this open office area, we have a terminal called VAV, variable air volume. And this VAV is responsible for maintaining the indoor thermal condition at a comfortable level. Like the figure shows here, the indoor air keeps around 70 degrees Fahrenheit in the heating season. The open office area has a lot of people working inside, and it has 2 exterior walls. So we first developed a thermal model using this space. The method that we use is called thermal resistance capacitance network. It uses an analogy between the electrical network and thermal network. This image here shows a 3-node network. If this figure represents the electrical network, then the driven power of the energy flow between the nodes is the voltage difference. And if it is a thermal network, then the temperature difference causes the heat flow. The thermal resistance represents how difficult for the heat to be transferred, and capacitances represent the node's capability of storing heat. This RC model is a reduced order model to represent building thermal behavior. And since all the parameters in the model have physical meanings, it is good for us to understand the building characteristics. So in this open office area that I mentioned earlier, we developed this RC model consisting of 4 nodes, 4 resistors, and 3 capacitors. The nodes are the outdoor air, indoor air, and 2 exterior walls. The resistances represents the heat transfer in the form of radiation, convection, and conduction. And the capacitances are indicators of how much heat the wall and the indoor mass can store. For example, the capacitance of the wall is determined by the thermal properties of the materials that the wall is made of. Some other heat input sources come from the sun, the solar radiation, the HVAC system, and the internal heat load. The internal heat load includes heat generated by human, electric devices, lighting, etc. For these nodes, we use differential equations to describe the energy balance of them. This can later be used to develop the model. The input-output dataset we use in this model contains all the variables in the differential equations. In the training phase, we use all the known parameters to find the optimal values of the unknown parameters that are the R's and C's. And in the testing phase, we use all the inputs to predict the output parameter, the indoor air temperature. Here is a flow chart showing how we implement the model. We first transform the differential equations to a state space form. The state space matrix is easier for the program to process, and then the initial values of the R's and C's are estimated and input along with the training data set to the matrix. The program uses an algorithm called SQP to train and get the optimal values in each iteration. The evaluation measure is the sum of the squared error between the predicted values and the actual values. When the program thinks this function has got to its minimal value, it stops and outputs the RC values. Otherwise, the program will try to find another RC value set within the bounds. The bound is set to be 1/10 of the initial values to 10 times of the initial values. When the optimal values of the R's and C's are found, they are then imported to the state space matrix along with the testing data set. We can now make the prediction on the parameters that we want and use certain evaluation measures to see the accuracy of our model. Here are some of the model results. In a time range of 7 days, from November the 11th to November the 17th, the predicted indoor air temperature has a similar trend to the actual temperature. The relative error of the predict values fall mostly in the 1% bucket in the histogram. And all the data points have a relative error less than 10%, which leads to a total RMSE of 0.27, which means the model has a 0.27 error when predicting the indoor air temperature. Considering the sensors allow a measurement error of 0.2 to 0.5 degrees C, this model has a good accuracy. The RC model, however, has some limitations. The first thing is that we need to install extra sensors to get the wall temperatures. And different buildings will have different RC structures and values, so the model cannot be directly used in other facilities. This problem will be addressed in our future work.
Okay, let me conclude our work in the past 4 and talk about the future work. So, till now, our Purdue data lake is ready for integration. So it's up running. So that means our streaming data can be later on directly integrated our model. Then so for online energy audits and energy optimization. Our data visualization tool is also done. It can be tested for other various data from other applications. Our heating and cooling AI model is ready for testing. So we have input for user to add in the most important input and information. So the model can be tested right now. The RC model works fine, have pretty good statistic accuracy confirmation, but we're gonna continue move on to based upon our experience and the major relationship between the parameters and the building performance to move on to the machine learning based model. So in the future work, we're gonna develop the cooling model, kind of refine the cooling model by using the new data going to be available in this summer. Then we will replace our RC model by data-driven building thermal model. we're gonna integrate all our submodels into with the Purdue data lake and make it available for other similar facility, and generate a more user friendly dashboard, working with the other group at Purdue to make it more user friendly. And the last one, we're gonna try our first energy conservation strategy, which is the pre-cooling method, to see how much, and test to see if we can reduce building peak load and save energies. So yeah, that's our presentation. Now we are open to the questions.
Are there any questions?
I'd ask a question. Ming, I'm sorry, Vikram, please go ahead. I'll ask after you.
Oh, thank you. Yeah, I was curious about, and maybe I have missed this. So in the RC model, there were some unknowns, right? Resistances and capacitance. How did you determine them?
Okay, DK, can you go back to your slides with the input slides, known, unknown? Yeah, right here. So that's the regression, right? DK, do you want to explain how it works?
So just like I showed here, here I use MATLAB as the coding environment, and this algorithm using SQP. So this model can iterate to get the minimum value of this function.
Mm-hmm.
So when they get, and when the program think it's the minimum value, then the RC values are at its optimal.
But the T in, which is the output you seek, right? The indoor temperature. That's the one you want to predict. So you need a series of these values to minimize this, or you are doing it on
yes, because the R's and C's are unknown at first.
Yes.
The R's and C's are representing the building characteristics. So we use this input and output to get the R's and C's. Then when we get the R's and C's, these are all known parameters. Then we use this circle here, these inputs here to predict this output.
And so the question is, when you do the final prediction, right, that the prediction you showed, that those predictions are done over new data set, right? The new indoor yes. values.
Yes.
And you're running it by using a different subset of the indoor temperatures. Is that right?
Correct. So also those R and C actually have the physical meaning, which really strongly related to the material that the actual facility used. For instance, the wall, if it is made by concrete, then R value, we have basically clue of the value where all those values should go. So that's basically build our constraints for those R's when program is searching for answer.
Mm-hmm. And just to follow up, can these be time dependent? So for example, if the temperature drops a lot from summer to winter.
Very good question. Exactly. So it's not time, it's presumably should be, because this is a super simplified model. So what we're planning on is we're gonna later on replace this by more strong correlated model, so that we'll have information of the season, even time into it. Yeah, as you know, this is very rough, right? Because highly lumped parameters here. Yeah.
Mm-hmm. All right, thank you.
Anis, do you want to raise a question?
I mean, my question was the same actually on the runtime dependency of these. So when the models have to be trained on the fly, how do we do that? But as you mentioned, this is what we're doing now.
Presumably it should be time independent. However, this is very lumped, so it does showing some variations along the time. So that's why so typically we have like a continuous train the model maybe according to the seasons, and we change in the model and upload it online. So it's like offline training, then update the online model. So it's more accurate in that way. Yeah. Any other questions?
Hi, can I ask a question?
Sure.
So in Kayla's presentation, it shows a correlation between the different input factors.
Yeah.
I just want to ask, did just use a linear equation to regress the two factors and get the correlation number?
Which correlation number are you talking about?
Just the AN model, the neural network model.
No, that Kayla's visualization is really reflect the relationship of data and the parameters. It doesn't have any machine learning concepts in there. So we just visualize relationship and data type, right? Is it integer or decimal? Because data, there are so many data and it has different hierarchy. We want to reflect the correlationship through the visualization tools. Yeah.
Okay, so this is a linear, just assume that these two vectors are linear relation.
Oh, you're actually talking about this, right? This.
This, like for example, this point 35, is that get by regressing a linear equation to between the energy consumption and the water return temperature?
That's a good question, and to be honest, I'm not entirely sure about that because I was generating the correlation matrices with built-in functions and didn't take as much time to look into the math that's driving it.
Okay, so maybe I missed some parts. And this correlation number is as one input in the neural network. Is that right?
No, this is just a reflect because we have a lot of parameters. We want to find out the most significant parameters, which we're going to include them in our actual learning model. So you may have thousands of data. Are we going to use thousands of data? That's our first question. We will only include the most significant parameters. So this is part of the data processing, what we did at the very beginning. So through this heat map to reflect the most significant parameters that we are include in this model. As Andy present the next slide, so Andy's model actually asks a user, put in what's your minimum correlation value. Then that can kind of cut a line, say, okay, if the correlationship higher than that value, we're going to include those parameters. If it's lower, then we just exclude all those parameters. Yeah.
If you go back once. Oh yeah, sorry, you go.
I just have a following question. So it's just to use the correlation to decide which one is most important and exclude the less important factors in the neural network.
That's correct.
And so in the neural network, is it possible to let the neural network itself to figure out which one is the important, which one is less important?
Is it possible to build a neural network with all of the inputs in the model?
Yes.
Yeah, that's that is something you can do, but you know,
Yeah,
at that point,
Yeah, I guess Andy trying to explain, we had a discussion about this, right? So this is always the balance between the calculation speed and you know, how many of the parameters should we include, right, Andy? Do you recall that? Yeah.
yes.
Okay, yeah, thank you. Mhm.
Okay.
Yeah, thank you.
Does Vikram still have a question? I see his hand is still raised.
Yeah. I have a question for you actually on this topic. So, similar to what I think Wanhui was asking. So you eventually narrowed down to 5 input parameters, right? These flow, output, temperature, building load, and work schedule. And when you make the prediction for energy consumption, you take the input at only one time, right? Or is it an average over many time discretizations, days, or something like that?
I'm using all of the energy. I'm using all of the data points. I'm not taking an average. So like we have for like the December data set, we have I think over 6,000 data points. I'm using all 6,000 data points for building load, heating, water supply, temperature as an input. I'm not taking an average of those values at all.
I see. So if you show the graph again, you have the predicted versus actual graph. If you can.
Oh yeah. That's gonna be slide. Okay, over here. Yeah.
So here the predicted value is for the predicted value of the energy consumption on a given day. Is that right? Or
yeah, you could think because so it is going to be a certain day. Like if you look at one of these data points, but it's so each of these data points is per second. Mm-hmm. So that is something that I was working towards to try to filter that out into the model in order to produce these figures such that it showed instead of like I see what you're saying, like it's just as actual versus predicted. I was trying to develop a figure that showed the progression of time throughout the model, but the problem with that is this model is built with the input parameters that I use, and if I can't really include time or like the date as an input parameter without or not with my understanding yet, because it was messing with my model. So basically, yes, you can think of a data point as a day, but there are multiple data points that are on the same day here.
Sure, but the main question is if one of these points is an energy consumption on a given day, let's say at a given time stamp, the input to that is also the the flow, the building load, the work schedule for that day, or is it for the preceding several days, let's say? That's the question.
Oh, it's for that day at that moment in time.
I see.
So like yeah. So if we're pulling it from like Christmas Day, we're looking at Christmas Day at 11:45 in the morning. We're pulling all of those values that we collected from 11:45 at that, but like what's the value there exactly? Because that's what we're capable of pulling from the EMC squared building.
Okay, all right, thank you.
Mm-hmm. Any other questions?
Okay, well, if there are no other questions, then I would like to thank Dr. Ming and her team for a very good presentation. And we will make recording of it available and send it to everyone. We will host it on our AnalytiXIN YouTube channel, where the rest of them are as well. So thank you again for attending and for listening and for all of your great questions. And yes, Dr. Ming, as Mitch has mentioned, great job as usual. Thank you so much for presenting today.
Okay, thank you. Bye-bye, everybody.
All right, thank you.
Thank you, everyone.
Thank you.